Okay, notice that when 2 as our endpoint, 2 was ruined from being a local minimum. That spoiled the party. 2 wanted to be a local minimum, but 2 was an endpoint, and that spoiled the party for it. But notice that if we don't read all this, please, but notice, just go right here where my cursor is, please. If we extend just by a little bit, if we extend our domain out to 2.01 and keep everything else fixed, then x equals 2. Well, now 2 was not our minimum, it was the location of our minimum. Please understand, it's the x location of our minimum. Our actual minimum was negative 79. 2 was the location of it, okay? Because remember, f of 2 was negative 79. 2 is the location of the minimum, and f of 2 gives you the minimum, the y value of negative 79. Okay, the x equals 2 is the location of the minimum, which is y equals negative 79. Okay. Now, go back down. But now if we could just extend that domain out, not by much. You could even make it tinier than this. You could say 2.00001. I just chose 2.01 just for spite, okay? But anyway, 2.01, that's arbitrary. There's nothing sacred about that, okay? But anyway, 2.01. Now with this, if you do this, but now don't go any further left on me, okay? Please. Now, the trick is not to go further out to the left. Pretty please. Now, with it like this, if x equals 2 will be the location of my absolute minimum again, it will still be my absolute minimum, and it will be my local minimum. X equals 2 will be the location of my double winner, absolute and local. And negative 79 will be that minimum value. Yes. Now, if you extend out to the right, I don't think you'll do any harm, because I think you might not do any harm if you extend out further to the right, because by that point, now f of 2, well, let me see, f of 2 gave me negative 79. Well, no, yeah, if you extend it out further to the right, let's see what happens. The first derivative, if you go further out to the right than 2, f prime is positive, you're going to be increasing from now on. F prime will stay positive, so you're going to have to be increasing. So yeah, you have f itself has nowhere to go but up. So, yep, you're good to go. Remember, if your derivative is positive, well, there's a rule that says, if I've not told you this yet, you can just look at the graph. If I may not have gone over this yet, but there's a rule that says that if just look at the graph. As it turns out, if f prime is positive, your function f is increasing. But that's actually the next video. I'm sorry to get ahead of myself. But just look. You can get technology. You can actually you can actually go out to trillion and you're fine. You can go further to the right and you're fine. It's going further to the left that's dangerous. But let's just not go there. Don't worry about going to the right. Now, going further out to the left is dangerous. If you go any further out to the left, you run into problems. Like if you extended the interval, if you extend out to 3, you're okay. I didn't really justify why you're okay. Just take my word for it. Now, if you extend out to the left, let's say you got to negative 5, you're in trouble, because let's say you plug in negative 4.5, you get something less than f of 2. Now, it's not your minimum being a local minimum. This time it's not localness that's in trouble, it's absoluteness that's in trouble. Guys, once you, as long as you keep the 2.01 here, as long as the right side goes past 2, your localness is good. You'll have x equals 2 will be the location of your local minimum forevermore. It's safe. It doesn't matter. It doesn't matter if you go past negative 4 to the left, as far as local minimum goes. Now, as far as absolute minimum goes, yes, it does matter. You know, if you go past negative 4 to the left, it might, and I'm pretty sure it will, ruin your absolute minimum. If we go past negative 4 to the left, in general it will anyway, because in general, if you go past -4 to the left, you run the extreme danger of it running, basically if you go past -4 to the left, x equals 2 runs the extreme, it actually runs the likely danger. In fact, I think it will lose its status as absolute minimum. The reason I'm trying to skirt around the fact I've not gone over some stuff that would that's coming up in the next videos. Okay, that's why I'm a little dodgy right now. But let me go up here and look. But at x equals, yeah, at -4, what happens? Yeah, at -4, I'm decreasing. So I would be decreasing. Yes, but I've not told you how to deal with that yet. So just take my word for it. Yeah, if you extend any at all, even the smallest amount that you could imagine, if you go just the smallest smidge to the left of -4, x equals 2 will lose its status as the location of your absolute minimum. It will, guaranteed. It will. So if you take this interval and you extend it, if you take the domain interval, now keep 2.01 here, or just say this is some number. Let's say your right endpoint is some number greater than 2, strictly greater than 2. Okay, and let's keep it to a closed interval here. This is a closed interval. Your right endpoint is a number greater than 2. Now, let's say that your left endpoint is, as long as it's -4, we're golden. X equals 2 is both the location of your absolute and your local minimum. Now, if you extend to the left of -4, as far as x equals 2 being the location of your local minimum, it's fine, no worries, because local doesn't even care. But as far as x equals 2 being the location of your absolute minimum, it's over. It's not anymore. You lost. It's no longer. Because let's say you go out to -4.01. Then if you plug -4.01 into f up here, it will give you something even more negative than -79. And x equals 2 has hence lost its status as the location of your absolute minimum. Now I use something a little different. I extend out to -5. And just for spite, just for show off, I extend out the rightward I go out to 3, but that's not necessary. That was just overkill. But anyway, if you plug in f of -4.5, sure enough, plug it into here and you'll get something less than -79. So f of -4.5 is less than f of 2. So you got to watch out when you extend. You don't endanger locality. When you extend to the left there, it's not the localness you endanger, it's the absoluteness you endanger. So that's some good critical thinking for you. Okay. So the local minimum, so the x equals 2, as long as you keep, something greater than 2 at that right endpoint, local minimum status was safe. Even if you did extend to the left of -4. But the absolute status was not safe. But that's all for that. So let's move on, please. Okay. So consider the function f from the closed interval -3 to 3 to r such that f of x equals x squared. So now the extreme value theorem is going to apply. We're continuous on a closed interval. So f prime will equal 0 if and only if x equals 0. Now, if we check the endpoints, if we plug in either endpoint, we're obviously going to get f of 3 and f of -3 both give 9. And, this is an increasing function, so the absolute maxima is 9, and it occurs at x equals positive -3. The absolute and local minimum, singular, occurs at 0, and that minimum is itself y equals 0. Okay. So there's that. And if we do the function from -3 to 4 into r such that f of x equals x squared, the only thing different about this that's a little strange is I'm going to 4. Now what's going to happen is f of 4 gives me 16, f of -3 is 9. 16 is going to overpower 9, so my absolute maximum, singular, is 9. I mean, no, back up. My absolute maximum, singular, is 16, not 9. 9 is actually useless now. He doesn't really qualify for anything. So 16 is my absolute maximum, and 0 is still both my absolute and local minimum, and 9 is just out in the code with nowhere to go. So that's all. And if I consider the function from -3 to 3 such that f of x equals x squared for x greater than or equal to 0, while f of x equals the negative of x squared for x less than 0. Now, f prime of 0 does exist, and it does equal 0. You got to push the limit. You can't use a shortcut. You push the limit like this and like this, okay? Remember? I almost know we've done this in times past. Now, f prime of x does not equal 0 for any other x value, since by the shortcut law, f prime of x equals 2x for x greater than or equal to 0, and f prime of x equals -2x for x less than 0. So by the shortcut laws, f prime can't be 0 if x isn't 0, okay? Furthermore, okay, so what we're saying is the derivative can't vanish anywhere but 0. It exists everywhere, it can't vanish anywhere else but 0. So basically the only place we can have local extrema is x equals 0, and f prime of 0 is 0 by the limits that we pushed here. The one-sided limits do exist, they agree, they equal 0. So our derivative is 0. Okay. Or the difference quotient limits, that is. Also, f of -3 is -9, f of +3 is 9. So our global minimum occurs at -3. Our global maximum occurs at 3. Okay, but what about x equals 0? Uh-oh. So guys, it's not a min or max. Note that f of x is less than 0 was a critical point. You know, f prime of 0 did equal 0, but it's you know, we didn't have a min or a max. It's what some people call a saddle point. We didn't have a min or max that occurred there. Note that f of x is less than 0 for x values to the immediate left of 0, and f prime of x is, or not f prime, just note the ordinary f of x is negative for x values in the immediate left of x equals 0, and f of x is positive for x values to the immediate right of x equals 0. So x equals 0 is neither a min nor a max of any kind. So even if you know if f prime of a point equals 0, that doesn't imply that that point is the location of a min or max. If the location of a point is a min or a max, then yes, f prime of that point will either equal 0 or it will be undefined. But the converse is false. Just because f prime of a point is undefined or 0, that doesn't mean that that point is that x point is the location of a local min or a local max. You can't go backwards with it. Okay. It might be, but it might not be also. You don't know. Okay. The converse is not true in general. You can't bet on it necessarily being always true. There's cases where it is, but there's cases where it's not. Okay. So guys, that's all. I hope that helped. This was a pretty hard lesson, but I hope maybe you learned something from it. And I'll try to create some quizzes pretty soon. That should be about it for Extrema. That actually should be all for Extrema altogether. Thank you, and we'll start another lesson, and I'll see you on the next video. Bye bye.